Hi, I'm Jeeves Tobbs with Orange Computer. Today I'm joining you at our first ever FPAA Worldwide Conference to tell you about some exciting new things we've learned. Let's get started. We first choose to analyze a common source amplifier. We start with the subthreshold expression for channel current as a function of gain voltage and drain voltage. Since the source of the NFET is grounded, we know that the two free parameters are input, gate voltage, and output, drain voltage. We can then linearize the expression, noting that the right-hand term is necessarily constant, and come up with a gain of negative kappa over sigma. Of course, ideal current sources do not exist. Instead, we may approximate a current source with a transistor. We may still equate the currents through the two channels. Following the same steps as the ideal current source, we take natural logs to linearize the expression, taking derivatives, and get an expression for gain. The effect of this second transistor is to lower our gain.
The common source amplifier was simulated for different biasing. Increasing bias did not really change the gain, it just moved the region of high gain. You can see how when the output is within 100 millivolts of VDD or ground, one of the two transistors drops out of saturation and we get no gain, seen here. Because the gain is so high, our region of gain is less than 100 millivolts. Taking just one of the previous curves, we performed a linear fit to calculate the gain. The black line shows the resulting curve. The slope of this line was negative 117.
We now move on to differential pair analysis. It is assumed that the biasing transistor here is subthreshold, so the current through both of these must be subthreshold as well. To derive the currents, we use KCl and the IV characteristics of these subthreshold transistors. There's only one free parameter in the system, the drain voltage here, so we can determine the I2 in terms of I1 to eliminate this free parameter. The differential amplifier consists of the previously analyzed circuit and a current mirror. I1 is the mirrored across, forcing the output to be I1 minus I2. It turns out if we substitute the expression we calculated for I1 and I2, the result can be written as a hyperbolic tangent function, or tanh. To simplify analysis, we apply the assumption that the differential input is small. In this limit, the expression for output current becomes linear, and we determine it from the transconductance of the amplifier. With expression for output voltage and output current, it is straightforward to determine output resistance. We can also see that the voltage gain is simply the product of these two.
To calculate transconductance, we hold one input voltage constant and sweep the other. We can then determine the output current through this voltage source here and graph it against voltage to get a transconductance curve. We can then do a linear fit to determine the transconductance value. The result of the transconductance sweep is shown for different values of constant negative input voltage. When a positive input voltage is near the negative input voltage, we have a region of high transconductance. As expected, when the two voltages have large difference, the current saturates to plus or minus the bias voltage, as we expect from the tanh model applied earlier. Taking one of the curves, a linear fit was done in the high gain region to determine the transconductance. Using typical parameter values, we expected that the transconductance to be around 14 nanosiemens. Our linear fit gave a slope which corresponded to 8.9 nanosiemens, which is still on the same order of magnitude. To calculate the output resistance of the OTA, we hold both inputs constant. It is important that the input difference is small so that we operate in the high gain region. Then we sweep the output voltage using a voltage source and measure the current passing through it. A plot of our output current versus output voltage can be curve fit to determine the output resistance, which you can see here is about 260 gigaohms. At the voltage extremes, the transistor's left saturation and the conductance rose. In the gain region, here, the amplifier exhibits a very low output conductance or very high output resistance. From typical parameters, we expected the output resistance to be on the order of gigaohms, which is what we got.
An NFET source follower we designed in Scilab is shown here. The lower transistor is a current sink. The output of the upper transistor needs to remain above 100 millivolts for the lower transistor to operate in saturation. If this transistor is in saturation, the voltage gain to the output will be approximately kappa, as demonstrated in this plot, which is output voltage versus input voltage of the previous circuit. When the input voltage reaches about 0.5 millivolts, we start to see some funny effects in the voltage gain here. Displayed are the results of a real-time measurement of output voltage against input voltage for a source follower, as you see in this circuit here. The lower curve is biased with 1.7 volts, and the upper curve is biased with about 2.4 volts. This result is strange as we expect a lower bias voltage to move the curve to the left, not upward. However, considering this to be an inaccuracy in ADC or something similar, we continued with a curve fit. In the gain region, both curves had a slope of about 0.7, which was on point for our calculations. As the source voltage decreased, or as VDD minus the source voltage increased, the slope of the curves tends to become steeper. This tells us that kappa increases with source bias. This is because as source bias increases, we get less depletion capacitance.
We simulated the common source amplifier. Now, we will actually look at measured data from the remote system. The common source amplifier was compiled and we performed a sweep of the input voltage to find the high gain region. The transfer characteristic matches previous simulation results, showing a high inverting gain here. After locating the gain region, we performed a fine sweep in steps of 1 millivolt near that input voltage. Even at this resolution, we did not get any points within the gain region. Performing a deterministic linear fit between the 2 points at the edges of the gain region would determine a gain of about negative 218. The output voltage was measured versus input voltage for the OTA in an open loop configuration. The negative input was held at 1.25 volts for the sake of symmetry. The plot is shown versus differential input voltage. As expected, we see a very high gain with differential input near zero. As the input increased, the output saturated to VDD or fell near ground. In order to calculate the gain, we attempted to do a fine sweep near the gain region with 1 millivolt steps. Again, this resolution was still not enough to get data points in the high gain region. The OTA was connected in a voltage follower configuration, and its input voltage was swept for its transfer characteristic. When the input voltage was near ground, inadequacy in the measurement system prevented good measurements. When the input voltage got near VDD up here, the transfer curve plateaued. In the linear region, a curve fit gave a slope of about 0.95, which is a reasonable gain for a follower. The follower integrator is so called because it exhibits first-order characteristics. In the event that a capacitive load is present, for example an output pin capacitance, a differential equation for the output voltage can be written. This differential equation is the canonical representation of a low-pass filter, which behaves like an integrator at high frequencies. With a small step in voltage, the response of the follower integrator is effectively a first-order exponential. The results of transient measurements for two different bias currents are shown on the same plot. The vertical offset was most likely due to problems during A to D conversion and does not affect calculations or the time constant. Focusing in on the rising portion of the waveforms, we subtracted the final DC values and then took the log of the result. This allowed us to perform a linear fit and calculate the time constants. At 100 picoamp bias current, the time constant was 24 milliseconds. We expected a doubling of the bias current to half the time constant. This was not exactly the case in our calculations.
As applied to the follower integrator, we can see the voltage rises linearly instead of exponentially. Here, we see the response of against the large step, where we see no appreciable difference in rise times and fall times. Enhance. As we zoom in, we can see the different bias currents impact the slope of the rise time. After performing curve fits, we discovered that the slope of the 200 picoamp bias was approximately twice the slope for the 100 picoamp bias. This agrees with our previous analysis. These slopes are equal to the bias current divided by the capacitance of the load. Thus, the capacitance seen by the circuit was around 15 puff.